Thanks a lot, Rainer, for your kind introduction, and good morning, everyone. So, as introduced before, my name is Maxime Chambonneau, working at the Institute of Applied Physics at the University of Jena in Germany. And today I'm going to try to show you how understanding nonlinear propagation in silicon may lead to some new applications, especially for joining materials together. First of all, I would like to thank the organization committee for giving me the opportunity to deliver this invited talk. That's really a great privilege to be here in San Francisco for showing you those results. All right. So basically the outline I will follow is, I would say, quite straightforward. First, I will give some words concerning the context of microfilamentation in silicon. And then I will speak about the applications we have devised concerning silicon to metal and silicon to silicon ultrafast laser welding. All right, so to put everything in context, it will probably be a secret for no one here that ultrashort lasers represent an extraordinary tool for modifying materials. And the reason is somehow contained here in this figure, because at those extremely short pulse durations, so below a couple of picoseconds, it is possible to separate the causes which are related to the energy deposition from the consequences which are related to the material response, as illustrated here. And this provides a fantastic degree of control on the modifications you can achieve in dielectrics, especially in glasses, leading to a lot of applications in fiber optics, in surgery, also in microfluidics, micromechanics, in data storage as well. And of course, the results I will present concerning more or less additive manufacturing and laser welding. So the main question now is, can we easily transpose everything that we know from dielectrics to silicon, right? On the paper, the problem looks quite simple. You just have to tune a little bit the wavelength and change the sample. However, if one tries to directly transpose everything that is known from dielectrics to silicon, then they will face two major problems. The first one is here, because we reached the technological frontiers. And as you can see here, silicon is not transparent to visible light, so we need for ultra-short laser pulses that necessarily emit in the infrared. And it appears that in this spectral range, the optics and the detectors are both most costly and less efficient in the infrared than in the visible range. But if it was only about technical difficulties or technological details, then it would still be possible nowadays to transfer everything that is known from dielectrics to silicon. Now, the main problem actually originates from physical limitations, especially when you have a look to the nonlinear refractive index of silicon. It is about 100 times higher than the one of glasses. What does it mean? It means that at relatively modest peak input pulse energies, there will be this competition between Kerr effect, which self-focuses the beam, and like this competition with plasma defocusing. So when you focus too tight, then a plasma is formed, and then this plasma will defocus the beam, then refocus, defocus, and so on. This is what we call the filamentation regime. And this regime has basically two major consequences. The first one, illustrated here on the left, is a nonlinear focal shift. As you can see here, when you increase the input pulse energy, then the focus is shifted upstream towards the laser. And the second consequence is intensity clamping, meaning that when you measure or simulate the maximum fluence you can deliver in the bulk of silicon or in the bulk of the material as a function of the input pulse energy, then at some point it will saturate. And when you take those two consequences together, well, one can simply conclude that there is a strong delocalization of the energy deposition, preferentially towards the pre-focal region. Okay, so now this is probably the most important figure of my talk, actually. If one tries to compare dielectrics and silicon, so basically one can represent the maximum fluence that can be reached in the bulk of the material as a function of the input pulse energy. And for dielectrics in blue, you can see that it is possible to cross the modification threshold of dielectrics. And for silicon in red, well, because of filamentation, we have this saturation, and it appears that this saturation is below the damage threshold of the material. In other words, if one tries to simply modify the bulk of silicon by a simple increase in the input pulse energy, then this strategy is doomed to failure. So, okay, now the main question is, what about the fluence remaining at the exit surface of a silicon sample? Is it sufficient for envisioning applications? And this is what I will address in the second part of my talk concerning silicon to metal ultrafast laser welding. To give you some words again concerning the context of ultrafast laser welding, one has to know that joining materials is something absolutely essential for the industry, and to do so, one may use some traditional methods, such as adhesive bonding, brazing, they are all listed here, anoding bonding, and so on. However, those methods usually suffer from important drawbacks. For instance, they may require another material or pressure resistance, or they may face some aging or degazing problems, or they might be just not resistant enough to high temperature environments. As a very nice alternative, which was developed in the couple of past years, the ultrafast laser technique was developed, and it consists of energy deposition at the interface between two workpieces. Then melting, mixing, and resolidification occurs, in turn leading to the creation of strong bonds between the two materials. And, well, in conclusion, this is a clean, fast, and contactless way to join two materials together. This ultrafast laser welding technique was shown to be applicable in many, many material configurations, such as glass to glass, glass to semiconductor, glass to metal, polymer to polymer, and more recently, it was published in Science here, to ceramic to ceramic. However, in the semiconductor to metal configuration, there was nothing too convincing so far. So let us have a try. Well, to do so, we'll employ the setup depicted here, relying on around 10 picosecond pulses at 1.55 micron wavelength. At this wavelength, silicon is transparent. Then we attenuate the energy optically with a half-wave plate and a polarizer before the beam is focused at the interface between silicon and copper by means of an objective lens. This objective lens here is also part of a microscope working in reflection and in dark field, and it allows us for positioning the geometrical focus with respect to the input surface of silicon. And then after the laser processing, we evaluate the bonding quality by means of an indenter connected to a force gauge. All right, so let us have a first attempt, and let's try to simply position the linear focus at the interface between silicon, and here metal is illustrated by copper. Let's set the input pulse energy to 300 nanojoules, okay? And now we measure the shear joining strength, which is on the order of 30 kilopascal, all right? What about now doubling the input pulse energy and go to 600 nanojoules? Well, then the shear joining strength, interestingly, is 10 kilopascal. So you double the input pulse energy and you got 3 times less shear joining strength. This behavior is strange and interesting, but the main question is that sufficient? I mean, can we say that the two samples have been bonded by the laser? And sadly, the answer is no, as in that case, the samples are easily separable by hand, and moreover, the typical values that can be achieved for other material configurations or with traditional bonding methods are on the order of a few megapascal. Okay, so why? In order to explain why we have such a result, we turn to nonlinear propagation imaging. And basically, we use the following setup depicted here. So we use the same objective lens as for the welding, the same silicon sample, and besides, we have a microscope, an inverted microscope actually, which allows us for recording the beam shape. And then by moving the focusing lens along the optical axis, one can reconstruct the 3D fluence distributions. And these are the results you can see here on the right-hand side of this slide for different input pulse energies. So on those results, one may distinguish three different regimes. The first one for very low pulse energies, lower than typically 10 nanojoule. Well, we are clearly in the linear regime as confirmed by point spread function analysis. We carried out those simulations with the following open access and open source model developed by my colleague Qingfeng. So if you want to make such vectorial simulations, just feel free to check for this code. All right, then if we increase the input pulse energy to something between 10 and 100 nanojoule, then one can see that the focus unambiguously shifts upstream towards the laser as a consequence of Kerr effect. However, in that case, the overall shape of the focal region is conserved. And then what you can see here, when we increase furthermore the input pulse energy, like more than 300 nanojoule, we are clearly in the filamentation regime, especially for the highest pulse energy of 1 microjoule, where you can see those multi-foci, which are related to the focusing and the defocusing dynamics. Okay, this was the qualitative pictures, and then quantitatively one can easily measure with those these experiments the peak fluence in the bulk of silicon as a function of the input pulse energy, and those are the red points that you can see here, and one can see that at some point, like after from 30 nanojoule, then you can see that there is a saturation of the energy deposition in the bulk of silicon, and it appears to be below the surface damage threshold of silicon. So it's not possible to modify quite easily the material in that case. And then there is another interesting parameter to look to, which is the nonlinear focal shift, so how the focus shifts from the linear position. And this is represented here, again, as a function of the input pulse energy. And one can see that the nonlinear focal shifts becomes non-negligible for input pulse energies higher than 30 nanojoule. And it may reach around 120 micron for input pulse energies around 1 microjoule. Right, so the conclusion of that is that increasing the input pulse energy leads to an energy deposition which should be far from the interface. And in order to understand and potentially relocate the filaments, we turn to modeling with my colleagues SteliosTzortzakis and Vladimir Fedorov from Greece and Qatar. So we want to evaluate theoretically the nonlinear focal shift delta Z, which is here. It reads this equation here, where f star is nothing else than the sample thickness, and then for this ZNL parameter, it corresponds to Kerr effect, which is considered as a lens. And then with this, we can evaluate the ZNL by Marburger formula, where we have a first free parameter, which is a critical power for self-focusing. And we also took into account, we modified this formula because for silicon, you have to take into account the losses during the propagation. So we took into account the reduced peak power with this equation here, and this beta 2 star is the two-photon absorption coefficient defined for a pair. Okay, so how does it compare with the experiments? Well, delta Z here is shown as a function of the input pulse energy. And so with this two-parameter fit, we can see that the trends are very well reproduced by this solid line here. Noteworthy, when the losses, the nonlinear losses are not accounted for here, then we have simply the Marburger formula, which overestimates the experimental data. So this fit here means that the major physical mechanisms that are responsible for the nonlinear focal shift are correctly described. And moreover, we have benchmarked our approach by carrying out some nonlinear propagation measurements at a shorter pulse duration, like 0.86 picosecond, and we get similar results, so our approach is benchmarked. Now, back to the universe of welding, I should say. Here you can see on this graph the shear joining strength for two input pulse energies, 300 and 600 nanojoule, without in red and with in green precompensation of the nonlinear focal shift delta Z. And the striking feature on that figure is that when you precompensate for the nonlinear focal shift during the welding, then it leads to a much better welding. Okay, so what now if we keep this delta Z precompensation strategy and at the same time increase the input pulse energy? Well, basically the results are shown here in terms of shear joining strength as a function of the input pulse energy, where you can see that it is possible to reach around 2 megapascal for approximately 1 microjoule input pulse energy. And this is suitable for applications, and this can be easily explained by the maximum fluence at the interface as well as the energy reaching the interface, which is much higher when you precompensate for the nonlinear focal shift. Interestingly, here you can see that no welding is possible for input pulse energies below 100 nanojoules, which simply means that silicon to metal ultrafast laser welding is solely achievable in the filamentation regime. And this completely justifies our approach to characterize the nonlinear propagation. Okay, with this, I will move to the last part of my talk, where this is silicon to silicon ultrafast laser welding. Okay, so to make a short recap, so from the state of the art, we have seen that it is quite easy to modify, to join glass to metal because there is not much filamentation effects, and at the same time, you got some high absorption at the interface due to the free electrons of the metal. As we have just seen, in the silicon to metal configuration, then we still have some high absorption at the interface because of the metal, but filamentation has to be accounted for when processing the stack of samples. And when one wants to increase furthermore the difficulty level, well, one can turn to the silicon to silicon configuration, where you still have those filamentation effects, but you have no more metal, meaning that you have low absorption at the interface in the end. So the following question should be answered, like, can we transpose the ultrafast laser welding technique to the silicon to silicon configuration? Okay, so here is the reasoning we had. So from the literature, we know that it is possible with nanosecond pulses as well as continuous wave lasers to bond silicon to silicon, but unfortunately, the thermal runaway during the interaction leads to large modifications, which means that the samples may be heavily altered in terms of properties, optical, electrical properties. On the other hand, when you have pulses that are too short, then you got this intensity clamping phenomenon, and the energy deposition will be too low to modify both the bulk and the exit surface of the material. And here comes an interesting paradox, because usually optical contact is preferable when you want to weld two samples together. But if two silicon samples are placed in optical contact, then by definition, they will optically behave as they were 1, right? And then because of point 2 here, then one can conclude that no modification would be possible. As a nice way to sidestep this paradox, one may enhance the absorption at the interface by a first approach would consist of grinding the surface, meaning that the roughness of the samples would be increased. Then the field enhancement, I mean, there will be an enhancement of the electric field, and modifications would be possible, yes. But however, the optical contact cannot be achieved between two raw samples. So as a method we propose, we want to deposit now some metallic nanolayer at the interface between the two silicon samples, because then we have high absorption because of the free electrons of the metal through inverse Bremsstrahlung, meaning that the absorption would be exalted, and at the same time we can maintain the surface quality, so the optical contact should be theoretically achievable in that case. So, well, basically the experimental procedure is now quite straightforward. So first we do some sputtering on the bottom sample with gold nanolayer thicknesses between, let's say, 20 and 90 nanometers. And as a second step, we do the welding with the filament relocation, so we precompensate for the nonlinear focal shift, and at the same time, we maintain the optical contact during the welding. Okay, so here are the results. The first results, those are quite recent. As you can see here on this photo, for every film thickness, the samples seem to be joined. However, when you take a closer look with infrared microscopy, then you can see that when there is no gold nanolayer here in B, well, the laser has simply no effect. In stark contrast, when you have some gold nanolayer deposited at the interface, then one can see the laser return tracks clearly as the dark features here on this figure. We have also tried different sample thicknesses just to ensure that our method is not dependent on the thickness of the samples we would like to weld. And basically it works, as you can see here, for 1 millimeter here and 0.7 millimeter thick samples. Okay, now concerning the bonding quality. Well, intuitively, one may think that thicker films would lead to more absorption, right? Because there would be more metal, and then higher temperature should be reached, which would lead to better welding. And experimentally, I mean, in reality, it's actually the opposite. Like, thinner films lead to better welding. And one can reach around 4 megapascal for 20 nanometer films, as you can see here, for the shear joining strength as a function of the film thickness. In order to explain this, we carried out some laser-induced damage threshold measurements on the films, so only the films, as a function of the film thickness. And you can see that the trends are inverted. I mean, the two curves are quite mirrored. And this means that lower damage threshold it means higher strength. And this was recently explained theoretically by electron diffusion, which is in this case inhibited by the small film thickness, which then acts as a trap for the hot electrons. As you can see here on these figures, for a 20 nanometer film, you may reach 800 Kelvin, while for a 400 nanometer thick film, then you barely reach 300 to 400 Kelvin. Concerning now the properties of the welds, here it is displayed the total transmittance experimentally in red as a function of the nanolayer thickness. And what one can see here is that, unsurprisingly, the transmittance, of course, decreases with the nanolayer thickness. And to explain this, we turn to theoretical calculations with the transfer matrix method, with the following refractive indices, and we got basically an excellent agreement, as you can see here, between the simulations and the experiments. And this means that this means two things. First, the optical contact is still maintained after the laser processing. And moreover, and more interestingly, there is no additional absorption which would be related to the laser modified areas. In other words, the silicon optical properties are not heavily altered in that case. And with this, I would like to conclude my talk. So to summarize, we have seen that filamentation governs laser-silicon interaction in the POC. Also, silicon to metal ultrafast laser welding is possible when you relocate the filaments and you take into account the nonlinear focal shift. By adding a step of metallic nanolayer deposition, it is possible to even transfer this to silicon configurations. And moreover, in both cases, we reach megapascal bonding strength, which are compatible with applications. Before ending my talk, I would like to acknowledge my colleagues who helped a lot concerning this study from the Institute of Applied Physics as well as the Leibniz Institute in Jena, and also the funding agency. And if you are more interested in all this silicon stuff, you may check those recent publications we had. So this is a review on laser writing inside silicon. This is the silicon to metal ultrafast laser welding. And this is a preprint on silicon to silicon ultrafast laser welding. And finally, I would like to thank you all for your attention.